Hello everyone, my name is Changwon Che from the SOC Design Team 1, and it's great to be here with you today. I was invited to give the webinar for our team, and I thought carefully about what topic would be most helpful. The subject I choose is not too difficult, but it's something you can really understand well unless you have worked on a real project. That's why today I'll be talking about chip configuration management. Today's talk is organized as follows. First, I will explain why configuration management is important. Then, I introduce the main component, repository configuration, project guideline, version control, stage check. Configuration management can be defined as systematically managing and tracking all configuration and environment related to the project. In my previous video, I explained that our team leads this project through collaboration with many different groups. The main challenge we face include collaboration across multiple teams and companies, integrating dozens of IPs into SOC, interactive and incremental development, engineers unfamiliar with version control. Now, let's move on to repository configuration. First, what is a repository? A repository is basically a database that stores project files and the complete history of change. Then, what do we mean by repository configuration? It refers to the project level setup that defines how the repository is organized and maintained. In a typical project, we usually deal with 18 to 100 repositories. These repositories are categorized into IP, block, decay, and design methodology. Now, you may ask, what does block mean here? In the hierarchical physical design flow, block-based design follows the idea of divide and conquer in physical design. This means we divide a large chip into smaller blocks, design each block separately, including placement and routing, and then combine them all at the top level. So, in short, a block is a unit of physical design with clearly defined physical boundaries. And one block may consist of one or even multiple IPs. As I mentioned earlier, our SOC project consists of multiple repositories. To manage them more efficiently, we make use of feature in Git called submodules. Now, many of you may already be familiar with Git itself, but I know that not everyone has experience with Git submodule. So, in this slide, I'll give a quick explanation. A Git submodule is simply a way to include another Git repository inside a parent Git repository. Each submodule is an independent repository, which means it has its own commit history and its own branches. There are several advantages to this. Code reuse. Submodules allow central management and easy reuse of commonly used code or libraries. Separate version control. Because submodules have their own repositories, changes can be tracked and managed independently. This helps reduce merge conflict that often occur when many engineers are working in the same repository. Of course, there are also disadvantages. Difficulty in tracking changes. The parent project only points to the submodule, so it's not always straightforward to see what has changed inside. And complex dependencies. When one submodule depends on another submodule, dependency issues can quickly become complicated. So, while key submodules are powerful for managing large SOC projects with many repositories, they also require careful handling to avoid disadvantages. Project guideline. A project guideline defines standard methodology to make sure we have consistent environment and a uniform way of implementation across all IPs and blocks. The key content of the guideline include workflow, release note, design document format, directory structure, metadata file format, design file list, port naming rule, scene check automation, and in-house utility. Among these, let me highlight one important item, the release note. Release notes are documents provided whenever a new version is released. They contain important information about the version, and they typically include 4 sections: new features, addition of new functionality, enhancement, improvement to existing features, bug fixes, correction of errors or defects, known issue, current problems or limitations that users should be aware of. By following project guidelines like this, we can maintain consistency across the entire SOC project, even when many engineers are working together. Before we get into version control, I would like to first explain the concept of maturity level, or ML. In SOC design, a maturity level refers to a staged development process. Each level represents how complete, how stable, and how ready the design is. This gives both engineers and stakeholders a common framework to track the project progress from the very first draft all the way to the final takeout. As you can see in this diagram, there are 4 main maturity levels. ML1, initial RTL. This is just the very first draft of the RTL design. ML2, full-featured RTL. At this stage, the RTL has all the functions we planned to include. ML3, stable RTL. Now the design is stable and it has passed the key verification check. ML4, final RTL. This is the final stage, the tape-out ready version. By moving step by step like this, it's easier for different teams to stay on the same page, because everyone knows the milestone and what to expect at each stage. Let's talk about branch strategy in version control. A branch strategy is a defined workflow that specifies how code branches are created, named, merged, and maintained in the version control system. The main goal here is to ensure smooth collaboration, maintain code quality, and manage release effectively. By following a clear setup of rules, we can make it much easier for engineers across multiple teams to work together without conflict. You can see the table of branch names and their purpose. We have the design working branch for daily development and the design stable branch to keep the tested version. When Alter is ready, we use the design release branch to hand it over to the DB team. For TFT, we have TFT working and TFT release branch. For physical design, we use the PDI working branch. Finally, the official release branch is where the encrypted RTL is delivered to the DSP. It's also important to note that these branches are not used just once. They are released multiple times depending on the maturity level we talked about earlier. This staged release process allows every team to receive their right version of RTL at the right level of completeness and stability. Finally, let's talk about sense check automation. First, what is a sense check? It's an early verification step to confirm that the design meets page criteria before moving on to more in-depth analysis, such as functional verification or PPA evaluation. Sense check automation means we run these predefined checks automatically and then systematically evaluate their outcomes to decide whether they pass or fail. On the left, the diagram shows the workflow. Work starts in the working branch, moves to the stable branch after basic check, then goes through regression tests, and finally the results are shown on a dashboard. On the right, you see the sense check item, simulation, RINT, CDC, RDC, DFT, and stasis. Automation helps us catch problems early and keep the design stable for everyone. That's the overview of our configuration management flow, from repositories all the way to sense check automation. Thank you for joining today's webinar.